Chapter 4 is all about exponential and logarithmic functions. So we're going to start by discussing exponential functions. Before we do that, we kind of need to define what an exponential function is. So far in what we've been doing, we've talked about linear functions where we have a line represented by an equation y equals x. We also know that we've discussed quadratic functions. These are the parabolas where y is equal to x squared. But an exponential function is a function that looks like this curve right here. It's represented by the equation y is equal to base a to the x. Exponential functions either grow or shrink at a really fast rate. You typically think of an exponential function when you're talking about money, so money that I invest, or perhaps the interest rate on maybe my credit card. It's going to grow really fast. So it can be a good thing or a bad thing. One thing I want you to notice, though, as we look at these three functions that I have laid out for you here, in both the linear and the quadratic function, the variable x is in what I would call the base position. In other words, x is raised to the first power here in for linear. X is raised to the second power here in a quadratic. But notice that when I start talking about my exponential function, the variable, the part that changes, that x number that's changing, is now up in the exponential position, right? It is the exponent for some base or some number a. And that's kind of the difference between equations that we're used to seeing and what we're introducing here in this section. So, having seen what the picture looks like, let's kind of come up with our formal definition. We have the definition of our exponential function is listed as some function equal to a base raised to the variable x. Now, we got to be on the same term here for our vocabulary. I'm going to call this the base. It's going to be the constant. It's going to be a number that we're going to see. And then we have x, which is our variable in the exponential position or the exponent position. So x is going to be the variable. A, which is our base, is going to be a constant, and it's all equal to f of x, or in some cases y. That's how we're used to seeing it. Now we have some restrictions on this base a. The base a must be greater than 0, but it cannot be equal to 1. So these are the two requirements for the base a. Now you might ask yourself, why is that the case? How come the base a has to be greater than 0? Let's come over here for just a second and let's talk about a. If I let a be a negative number, a number less than 0, and I'm going to raise it to, let's say, the 1/2 power. Well, if you remember, if I have a number written in its rational form and I want to rewrite it in its radical form, then the base a, negative a, goes underneath the square root symbol and it's raised to the first power. So the denominator is the index and the numerator is the power. And that's how we would write that. Well, think back. Can I take the square root of a negative number? No, I can't. So this negative a to the 1/2 does not result in a real number. If I did the same thing here where I had negative a raised to the 3/4, remember the denominator is the index, so it's the 4th root of negative a raised to the 3rd power. So a negative raised to the 3rd power is still a negative. And so can I take the root, the 4th root of a negative number? And it follows the same thing as a 2nd root of a negative number. We cannot take the even root of a negative number and come out with a real value. So this doesn't work either for real numbers. So that's how come we're limiting our base a, or we're restricting our base a, that is, to all numbers that are greater than 0. In other words, no negative values. Now, what about the idea that a cannot be equal to 1? Well, think about that for just another second also. If I have some base, I don't know, 3, raised to the first power, then that is still 3. No, let me say that a little bit differently. Not raised to the first power. If I have the base 1 raised to the third power, right? If I want my base to not be equal to 1, I wrote it backwards. So if I want my base to be equal to 1 raised to the third power, that's still 1. If I have my base 1 raised to the 53rd power, that's still 1. If I have my base 1 raised to the 1,000,000th or 1,000th power, that's still 1. So see, if I have a base of 1, it doesn't matter what my exponent is because it's always going to come back as the number 1. So those are the two restrictions that we have on the base. It has to be greater than 0 and it just can't be 1. Now the next thing that I want to talk about, because we're going to be using the natural base of e in this chapter, so it's kind of nice to see where the number e comes from, or the base e. We're going to use it as a base. E is a number that if you were to look on your calculator exists. Okay, so just like pi is approximately 3.14159 blah 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 blah, the number e has a decimal representation which is somewhere around 2.7182 blah blah blah. And e comes from this expression right here. So in other words, if I were to take 1, add it to 1 over some value n, and raise the whole summation to that same number n, I'm going to get really close to this value, 2.718. And here's a chart that kind of explains what's going on. So if I were to let n be equal to the number 1, then if I plugged it into this formula right here, I come out with 2. And as I start increasing my value of n into this formula, then the number that is resulting is approaching this 2.718 blah 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 blah, kind of like pi approaches 3.14. So all of that is just to say that as we are moving through this chapter on exponents and logs, understand that when you see the letter E, it actually is representing the number 2.718. So you just need to know that for the future. Okay, and that is kind of our definition of exponential functions. Now let's talk about graphing in the next video.